thank you very much. Thank also the organizers to invite me here. I really have to congratulate because you pull up a very nice workshop. So I think so far was really successful. So thanks. And so I come from a slightly different field. So I started to do 2D materials only recently, and we tried to collaborate with Samuel. But at the end, nothing turned out, but there is still hope, right? So because we are coming from the photoemission field, so we didn't hear so many talks about photoemission, and this maybe I think will be the first just related on photoemission. And I apologize in advance. I will use some acronym during my presentation, and I will try to explain what the acronym stands for, but the most important one, I guess, is PEEM. And PEEM means Photoemission Electron Microscopy. It's an approach based on the photoelectric effect that we'll explain in the next slide. It combines spectroscopy and microscopy. So it's a technique that results into an instrument, and my idea, the aim of my talk today, is to prove you that this technique actually is quite interesting and can be used and exploited in order to measure and address properties of 2D materials. Although not all the examples that I will give are 2D material related, I think that anyway it will be, I hope, instructive. So the advantage of having spectroscopy and microscopy combined together is that we can access at the same time electronic, magnetic properties and also out of equilibrium state, and we can do this within the same instrument. And I decided to select some examples, key examples or application. The first one that I guess many of you would be interested in is so-called microprobing. So the capability of our instrument to look for example, flakes on our surface, find them, and locally measure electronic, magnetic, and dynamic properties. The instrument can also be upgraded, and you can perform also spin-resolved band structure mapping. So you can access the band structure of your material with spin resolution. And finally, if you couple it with the proper sources, you can also study the ultrafast dynamics of such systems. As I mentioned, PEEM stands for Photoemission Electron Microscopy, so it's basically based on the photoelectric effect. Here, what we do, we shine light, usually in the X-ray or UV regime, so extreme UV regime. And what we get out, if the energy of our light is high enough, what we get out are photoelectrons. And what we measure about our photoelectrons is the kinetic energy. And now, this well-known equation, if you know what is the photon energy, the Ward function of your system, then you can basically trace back what is the binding energy from where the electron came from. Now, if you complicate your setup a bit more, you can also measure the takeoff angle of your photoemitted electron. And if you measure simultaneously the kinetic, so the binding energy of your photoelectron and the takeoff angle, you can basically reconstruct the parallel momentum of your photoelectron. And therefore, you can directly map the band structure. This technique, also many of you may know it as angle-resolved photoemission spectroscopy. And here I just put a couple of examples of how the band structures of some materials look like. So that's a standard photoemission experiment, so nothing new here. We have a photon source. We excite our photoelectrons, then they reach our detector. And what makes PEEM special is actually this part here. So here I just put like a sketch of how complicated it is, because this is not a standard hemispherical analyzers, but there are some tricks in order to make it a bit more efficient. Because in PEEM, what we do, we don't simply collect electrons, but we also accelerate them. So you have your sample, you have your detector, and what you do here, you apply an extremely high electric field. So what does that mean? When the sample is grounded, you can imagine that you are photoemitting electron in the wall, solid angle above your surface. But now electrons see an electric field, and then they are accelerated towards the first lens. And here I just put some numbers. So if you use an accelerating field in the order of 20K, keep in mind that for these instruments, this is between 10 to 20K, depending on the instrument. Then this is how the trajectory of the electron changes. So if at no field, it would be emitted at 45 degrees. Then if the kinetic energy of this electron is 2 eV, then you see that the angle is pretty much shrink. And if you go higher energies, then it's still, let's say, very, very small compared to the 45 degree. And in this particular scheme, we have a great advantage. We can perform what is called parallel detection. So we can look, you have to think about it, it's not a scanning probe technique. but it's like more a camera. So you're really imaging something. And we can do it even with a decent lateral resolution, or let's say for the measurements that we have in mind, around 10 to 50 nanometers. This is how, so there are a couple of types of these instruments. This is one of them. This is called the NanoESCA. It's a commercial instrument. And that's how it looks like from the inside. And what makes PEEM special? So at the beginning, I mentioned that there is a combination between spectroscopy and microscopy. And what makes PEEM special is that he can switch between two operation modes. The first one is called imaging mode. And what you're doing here, you're mapping the lateral distribution of photoemitted electrons. So you shine your light, your photoemitted electrons are, are collected by the electron optics, and then we discriminate them in energy. So we select a specific kinetic energy of our photoemitted electrons, which, if you remember the first slide, it corresponds to specific binding energy. And what does it practically mean? It means that if you have a sample, for in this case, this is a chest pattern silicon sample with a gold pattern here. If you look at the binding energy where you would expect to have the gold electrons, then you can see laterally where they are distributed, and then you get some sort of contrast. On the other end, if you perform these spatial resolved measurements, changing the kinetic energy, you can select a region of interest and then extract, for example, spectra on a very specific part of the surface. And this, of course, makes it very relevant when you want to find your flakes and when you want to characterize, even from the chemical point of view or the magnetic point of view, your flakes, because this can be easily coupled with circularly polarized light, so even in the X-ray regime, and you can perform XMCD imaging, so having magnetic contrast in the real space. But you can do more. So what you can do, you can change the settings of our lenses here, and you can shift what you see in your detector. So you are no longer seeing the real space, but you're seeing what is the back focal plane. And since we're dealing with photoelectrons, the back focal plane basically allow you to access directly the parallel component of the photoelectron momentum. And here we do the same trick. We just change. So we have what we call two-dimensional momentum maps. We change the kinetic energy. So we just scan over the kinetic energies, and then you have a three-dimensional stack where in one plane there are the momentum, the parallel momentum versus the intensity as a function of the parallel momentum. And then you perform like cuttings along standard, along symmetry direction, and then you can reconstruct your dispersion relation. And now the talk. So I will just try to, having introduced the tool, just to try to tackle 3 different examples. And I would start, I think that microprobing in this community is quite relevant. So here, this is an example. This is a sample that we tested like long ago because we wanted to go to something more fancy, but at the beginning we wanted to really understand that the instrument was working. So Samuel provided us an hexagonal boron nitride sample, and that's a real space image. So what we see here, this is taken at the Ward function contrast, so I won't give too many details in that, but what the contrast that you see here rises for a difference of Ward function within your surface. If you compare this with the optical images, so Samuel could tell us where the flake was. So we have like, we play what is called battleship field, battleship. So basically you put some coordinates and then you look for your sample and you can identify the flake. And then what you can do, so you have your image and then physically you insert an aperture in your optical column. And this aperture basically selects a region that you're interested in and cuts off everything else. So photoelectrons coming from outer region of this aperture are simply hitting the aperture and they cannot go through. And then what you do in the same optical column, but after the aperture, you switch between the 2 modes, so between the momentum and the real and momentum mode. And therefore, you can have basically what I described before. So the electronic structure laterally resolved. So we are measuring the electronic structure of a flake specifically from a specific point on the surface. And again, you do the same trick, and then you get the RPES, the band dispersion that maybe you are usually seeing. This is another example how a measurement look like. So those are our measurements, what we see on our detector. I just took an example, a single crystal, and you can identify your surface brilliance zone, perform cuts along high symmetry direction, get the RPES, and then if you integrate for every energy the amount of counts that you have, what you can get is basically something which is proportional to the density of states. So those are momentum integrated curves. And back in the days, we used this in order to probe this direct to indirect band gap transitions when you change the dimensionality of your 2D material. This is an experiment done with the users in 2017 when I was still a PhD in the electrosynchrotron. And you can see how everything that I introduced so far actually is now helpful, because they came with this rhenium disulfide sample, then you had the B layer, the mono layer, then you had the thick part, all in the same sample. And then what we did basically was just taking spectra from the B layer, from the mono layer, and from the bulk. And we compared them to the literature, and sorry, to the to theoretical calculation. And then what they were able to demonstrate is that when you go from the mono layer to the bilayer, so in the mono layer it's an indirect band gap, and then in the bilayer it becomes direct. So, and this is one of the things that this instrument can do. In the other part of the talk, then now the question is, can I do this band structure mapping also with spin resolution? And of course, the answer is yes. So that's a standard configuration of our microscope. So now we are basically projecting the backfocal plane. So we have a momentum map, and this is in the direct column. Now we insert a mirror, an electron mirror here, which is a tungsten 100 crystal, and electrons are scattered on a different optical column here. And this scattering, depending on the scattering energy, is spin dependent. Now, if you properly characterize your sample, so sorry, your detector, and you know what is the Sherman function of your detector, what you can do is having like, you can directly quantify the spin polarization, and at the same time, you know also, let's say, the spectral width of each band. And again, you perform the same trick here. So you take a different kinetic energies, and then you scan it over, and you have this four-dimensional stack, and then you can reconstruct your spin-resolved band structure. So what we have now, it's this is a very funny color scale. So red and blue are spin-up, spin-down components, so the spin polarization, and then the intensity is basically the spectral width of the band. So it's not super intuitive to really look at this maps. And I would like to give you here a quick example how we use this spin filter process in order to, let's say, tackle a scientific problem. This is the part that goes a bit beyond, or let's say not beyond, but is not truly to the material related, because we did, as a model system, we investigated like an iron 100 surface where we actually passivated with oxygen. The motivation back then was that we wanted to grow interfaces where we have molecule in direct contact with a ferromagnet. And when you put a molecule in direct contact with a ferromagnet, usually what you have is disorder. So molecules do not self-assemble because molecule-substrate interaction, it dominates over the molecule-molecule interaction, which is the one that gives you the self-assembly. But then if you intercalate a layer of oxygen that really reconstructs in a very ordered manner, so you have like this one-by-one reconstruction here, then you can somehow decouple the molecule with the surface. But the first question that we had to answer is how actually oxygen modifies these iron properties. And this was something that was in the literature for long, but no one really tried to investigate with, so the data were like 20, 30, 40 years old, and, and no one really put effort in looking at it again. So here we'll try to quickly explain you what we found is that this is the single particle model. So here there are no electron-electron interaction. You have your oxygen atom from one side, and you have your ferromagnet from the other. When they are far apart, oxygen has its own very well-defined energy levels, and instead, iron has the D bands that are very localized, and then you have the S bands that disperse way more. You put the two systems in contact, and then, according to the norms of a Hammer model, what you have, you're forming bonding and anti-bonding states. And then the orbitals of the molecule, of the atom, or the molecule, they interact with the D bands. And if you do now, you put more molecules and you form an ordered structure, what you have is like a hybrid interface, where you have these adsorbate resonances that split in bonding here and anti-bonding. And in this model, basically, there is only minor influence on the metal density of state. So is this really the case? And of course, in order to check whether the single particle picture in this case applies, we needed to access the spin properties of the interface. But the first thing that you do is really looking at how the band structure when you put oxygen looks like and compare it with theoretical calculations. So this is spin integrated data. And you can see here, so we recognize the bonding states where we were expecting to see them. Then close to the Fermi level, we have a mixture of the anti-bonding states of oxygen and the iron D bands. And theory and experiment, they were matching, let's say, pretty well. And then we perform spin resolve measurements. And this is basically the result of spin resolve measurements in the same energy window. The problem here is that it's very difficult in this color scale to evaluate what is happening, because you have at the same time the majority and minority contributions, then you have the spectral weight of every band. So it's nice to show it in a publication, but if you want to quantify the splitting of the bands, the width of the bands, and all this kind of parameters, is much more difficult. But with the technique, basically, so this map is actually already data processed, and you can, let's say, disentangle separately the majority and minority contribution, and you can plot them. Separately, and that's the result. So in blue here we have the minority states. In red are the majority. So those are the same energy window, just for basically one spin contribution. So, we plotted the spin contribution separately. And what we can do now, we can basically take line profiles, so identify where the band is, and also fit it with some function. In this case, we just took simple Gaussian, and we can quantitatively extract some parameter. And what we observed that actually puzzled us a lot was that close to the Fermi level, you have a strong renormalization of the bands. Here, the spin split, the exchange splitting is drastically reduced. And at lower energies, instead, you have these bonding resonances. And the broadening of these bonding resonances is spin dependent. So there is one, the majority state are much broader than the minority state. And the question was then, this is captured by DFT, so in the single particle picture, and the answer, of course, is not. So here there is no strong renormalization of the D bands, and also the adsorbate resonances are not, let's say, they don't have a broadening which is spin dependent. So then we had to increase the level of theory that we were applying, and we asked our collaborators in Dublin to perform dynamic mean field theory calculations. The idea is that you take into account also electron correlation. And if you do that now, what you can appreciate is that you have a stronger normalization of the D bands, which is something that we observe, and then you also have a spin-dependent broadening of the adsorbate resonances. So the idea that we had is that, what we actually claim is that we increase, so by putting oxygen, what we do, we effectively increase correlation in such a material. And we come up with an explanation why is that so. And you can think about it, so I will try to quickly walk you through it now. So in the iron 100 surface, we have no occupied majority state. So it doesn't really matter from where you're exciting your photoelectron, but you can create, let's say, this photoelectron can only scatter with a core hole that is in the minority part. And then now, if you go to theory, you can just calculate what is the probability of this scattering event. And for the majority, excitation is proportional to the U, the effective Coulomb interaction. And from the minority, excitation is proportional to minus J. So the majority electrons are stronger correlated than the minority electrons. This, of course, changes when you put oxygen, because you have a different band filling now. And you move, basically, the bands up. So now you also have unoccupied states also in the majority bands. And, of course, you're opening up a new scattering channel. And this overall increases the wall correlation of the surface. So this is like the picture that we had in mind. Now, in the final part of the talk, so far, what I discussed were excitation. So we played a lot with the detector, how the detector can actually do or cannot do. But you can also play with the source that you're using. So far, what I mentioned was just static. So we used like light sources that are kind of static. So we have a UV helium discharge lamp. Synchrotron has some time resolution, but you are never really exploiting it. And then anyways, in the order of, I don't know, tens of picoseconds. So it's not really ultra fast. But what you can do, you can actually say, OK, no, I want to build an ultra-fast beamline, and I want to perform time-resolved measurements. So I want to look at the dynamics of our system. And this you can do it by using what are called this pump probe schemes. So what you do, you have two light pulses. One is the pump that comes first, and the pump excites your system. So it brings electrons out of the equilibrium. And usually what we require to our pump is that that is below the work function of the material. Otherwise, this would result in direct photoemission. And after a certain delay of time, a probe comes. And the probe actually allows us to probe the system at a very specific time. And what you can control very well is the delay between the pump and the probe. So simply by changing the optical path of the light. And then you have basically a screenshot of your system, how it evolves, how it reaches equilibrium again. The difficulty here is that, of course, we want to map band structure. In order to map band structure, you need to access high electron momenta. So if you're using pump and probe pulses, which is visible or visible, then, of course, then the total momentum that your electron will have won't be that great. And you cannot map the entire Brillouin zone. So the trick here is to go to what is called high harmonic generation. You take your laser pulse, which is in the order of 200 femtosecond coming out from the laser. You compress it down to 40, 50 femtosecond, and then you shoot it on a stream of argon gas. And then because of the high harmonic generation process, what you get out are odd wavelet numbers of the seeding radiation. And you can go up to very high harmonics, because that's why it's also called high harmonic generation. And you can reach energies, so with the decent flux, of course, people that do high harmonics can even go to 100 of eV. The question is how many photons you do have at the end of the day. And you can reach energies with a decent flux in the order of 20 to 40 electron volt. You need to monochromatize your high harmonic generation, because you have many harmonics in there, and then this you can do it with a multi-layer mirror without losing time resolution. And we can keep the time resolution pretty decent. And also the spot size of our beam, it's relatively small, which is an advantage if you also want to look at flakes, because otherwise you would just waste photons. Because if your flake is 20 micrometer and you are irradiating a millimeter, then of course you lose like 99% of your photons for nothing. And of course, the energy resolution here depends on how compressed the pulse is. And we applied this for different systems. I don't want to go into the details now. So we started first the hot electrons and their thermalization in the bismuth selenide. Recently, we also investigated this DD transition in iron PS3. And the other part that I'm focusing on right now is this. So basically, are the out of equilibrium feature of TM transition metal dechalcogenides. And in particular, now we are working with tungsten sulfide. So just here, I want to briefly mention what we're doing. I'm not trying to go too much into the detail, but what we do, we tackle the problem from two different sides. We grow from the one end. We want to have very ordered and high quality samples. So we grow some of these samples in situ. This has been done on gold 111, and then those are really single layer and extended samples, and then we do characterization with scanner entanglement microscopes. And also we characterize our sample with the PEEM that I showed you before. Those are just, that's for the bulk tungsten sulfide, but for the monolayer, it looks pretty much the same. Then we also studied the excitation. So let's say we studied the system out of equilibrium. This was like in order, that was the paper that we did in order to characterize our high harmonic generation beamline. And here I would like to point to the fact that, so PEEM, thanks to this parallel acquisition scheme, has a big advantage. So this is a single measurement. So this is not something that we have to scan angles or something like this. This is what we collect on our detector. And therefore, we have like really momentum resolution. So what you can do, this is like a momentum map. You can put a region of interest to one feature that you're really interested in. So those are unoccupied state free carriers that we excited at the sigma and k point. And you can track, let's say, with k dependent, so with k resolution, the dynamics at specific k points. And then you can see what is the relaxation depending on the part of the brilliant zone where you're looking at. And what we saw back then, it was that basically our pump fluence was too high, and then we couldn't form the excitons, but we had basically a mode transition, and then we were dealing basically with free carriers. I'm interested in all of this because the goal of what we are doing now is to engineer new organic transition metal dechalcogenized heterostructures. And from the one end, we want to look at new excitonic channels. So we are chasing these interlayer excitons. And there is already one paper on ArcSieve from the group of Stefan Matthias, where they have a type 1 alignment. And then they claim that they see an interlayer exciton. And we want also to modify the properties of our TMDs by on-surface chemistry. And for that, we are collaborating with a group of Avik Ghosh in University of Tromsø in Norway. And we already started to do some preliminary work. So now what we are standing at the moment is just, so we absorb our molecules. So we start with pentacene. This is on tungsten sulfide. And let's say here we have a preliminary characterization of our interface. Our molecules are very well ordered, so which is good for doing photoemission experiments. And what we see is that we have a type 2 alignment type 2 alignment heterostructure, which is slightly different to what they show here, which is a type 1. And with that, I really hope I convinced you that PEEM is a very nice tool for microprobing the electronic structure on the surface, that we can access the electronic and spin properties, and also we can also probe the excited outer equilibrium dynamics. And with that, I would like to thank my former group, to whom with what I'm still collaborating, and especially Mirko Cinchetti, David Yanas, and also the other guys that contributed to this work, theoreticians from Dublin, now in Venice, and then also the new collaborators in Graz. And I want to thank you for your attention.